Okay. Okay. So do you remember how to clone a repository? Yes. Oh, yes. Yes, we learned that in kindergarten. Oh, all right. So, okay. So you go to the GitHub website, you go the green button, click on the green button. It says clone. We need to copy the GitHub address. Then we go to HydroShare to, so we need to define where we want to put this project or this GitHub repository. So we can choose any location. So, but to clone it, we need to open a terminal first. Okay. And the command is git space clone, Control V to paste the address, and you click enter. Okay. So now we have a new folder that was created seconds ago. And in this folder, we're going to find 5 files, 5 Jupyter Notebook files. And that the first is the main, and then we have step 1 till 5. So what we're doing right now is cloning this repository I posted on GitHub. We clone it by copying the address and passing on a terminal git clone and the address of the repository. You can open the main Jupyter Notebook file. So this is part of a National Science Foundation grant, and the team members are there. So the goal was to create a tutorial that uses remote sensing and soil moisture data and machine learning to estimate spatially this variable. So the steps are a series of steps that will guide us on how to implement this. The idea of this repository is that you can replicate this effort on your term project if you need it. For example, let's go to step 1. The step 1 is the introduction to the project. A while ago, I wrote a paper when I was a student, and I was working on my PhD thesis in central Utah in an area called Delta, and I had to drive around collecting soil moisture data with a probe. There were different types of crops in every farm. So what I did for that project was I compiled all that data into a CSV file with the coordinate for every point and the date for every trip that I did to California. And then I create a machine learning algorithm. It was fun, uh, and we got good results from the machine learning. So how many years later? We'll say this was done 11 years later. I am revisiting that data, and I found that this problem could be solved with linear regression, which is good. A simpler model that can describe soil moisture on every farm location presented in this map. I collected soil moisture data in 4 dates: May 13, May 29, June 14, and June 30. Okay. So where is this data? This data is in the folder called ground information. We can double click on that file and we will see a table that has names for the fields, latitude and longitude, soil moisture values. SM means soil moisture for every date, temperature of the soil, salinity or electrical conductivity. And also we have the type of crop and a list of the sampling points. So in total, I have 80 variables or 80 samples. So in this field, I have, for the same coordinates, I took readings of soil moisture every on these 4 different dates. Okay. So to run this notebook, we need to install some modules. And what we can do is to copy these 2 commands that we have here, pip install -u Geemap, and we will install also the Eemont module. So we go to our terminal and paste it there. We do an extra enter to install the second library. Okay. So now we can run this notebook. Let's run the first notebook that says import pandas as PD. And you see that I'm reading the file, the text file that we just opened. We're using pandas because it's an excellent library that allows us to see complex tables. We can have text and numbers in the table, and pandas is just like our Excel in code form. So the explanation for every column is in there. The field, the custom name for the farm, the coordinates, the soil moisture values, soil temperature, electrical conductivity, the type of crop, and a sequential numeration of the points. Okay, so here is a question. You have a CSV file with coordinates and values, and you have Geemap that you have been using for the entire semester. How do I bring my data to Geemap? Okay. Well, first let's create a map. And as usual, I need my verification code. I'm going to, I can use any. Continue. Continue. Copy. Paste. Okay. We have our map. And so what I did before to create the map, I tried to convert that CSV to a shape file and it was very messy. The tutorials that I could find were giving me not good indication. So what I did beforehand is I went to RMAP or RGIS Pro, and from there you can convert any text file that has lat and long into a shapefile. That way I have a shapefile that has the information of the table, but now in a spatial format. So what we're doing here in the next cell is we're going to call that shapefile. Has the same data as the CSV, and there is a command called Geemap dot shapefile to Earth Engine. So as long we pass the location of our shapefile, we will get this variable that contains now my information now into Geemap. If I run this cell, now I see my different points plotted in the map. So I need now to get the satellite data. Notice that I only collected data for 4 dates. So I need those specific Landsat dates to use it in my area of study. What I do first is define an area of study, in this case a rectangle, with the upper left and the bottom right coordinates. And I can plot that area of study. Then I'm going, but that time, when I was doing the sampling, I also was looking at which satellite, what Landsat satellite was overpassing that day I was collecting the data. So my timing of those 4 dates coincide with the satellites passing overhead. So I can have a direct matching of my numbers with the values. So at that time, Landsat 7 was the available satellite, not 8, neither 5, only 7. So I'm going to run this cell that is going to use the Eemont library, and I'm going to pass filter bounds to search for data only on my area of interest. And I'm going to use this Eemont command called preprocess that is going to deal with the offset and the gain values. So the data, instead of being in a uint 16 scale, is going to be in float format. We have studied Landsat, and we have an idea based on the wavelet number which spectral region they belong: blue, green, red, near infrared, shortwave. So now we could use only this spectral information and look for a model that can say soil moisture is equal to a factor multiplied band 1 plus a factor multiplied band 2, like a linear regression. But we have studied over time, the spectral response of vegetation. We know that certain spectral regions carry certain type of information: red, green, blue related to chlorophyll, red edge regarding nutrients in the plant, near infrared is about biomass, shortwave is about water content in the leaf. So and so on, based on that information, hundreds of vegetation indexes have been created. So Eemont, the package Eemont, is compiling all those vegetation indexes for us. Probably the library has more than 200 indexes for now, and those are separated into applications like vegetation or fire or urban areas or geology. So in this case, I want to use all the vegetation indexes that are related to vegetation. And there are many. Okay, so now I have this Landsat archive that is related to my area of study, and every image in the record has these spectral bands or spectral indexes related to vegetation. How many indexes are there? Here I put a link so you can visit the Eemont package. So here we have the list of indexes. When I requested the vegetation indexes, these are some of the indexes they created. Currently, there are more. There are more indexes in this, so we will see it in a minute. But when I pass this command, spectral indexes vegetation, for all the images contained in this variable Landsat 7, it will calculate its respective vegetation index. So I need 4 satellite images. So what I'm going is now to filter every individual Landsat image per the date that I'm looking on. So I run this cell. And I'm going to add them to my map. It's taking a bit to plot my maps. There we go. So one of those images has a fire in it. This was in 2012. Some of the part of the forest area was burning. So you already know how to use this tool. So we can turn on and off the different satellite images. One thing that I want to make emphasis here is Landsat 7 has this issue. You see the stripes, the white stripes? Those are missing pixels. There was a malfunction in the sensor of the satellite that caused that the center of the image is complete, but up to a certain distance, those missed pixels occur up to the edge of the image. And this happened for all the Landsat 7 images since 2003, I think. So My area of study, which was this region called delta, happens to fall in that location where there are missing pixels. This is a problem for me later that was solved when I don't have pixel data in for my calculations. So now the next steps are, for example, how I can clip a Landsat image. I can have the entire image, or I can have just a region. The way to do it is you have the name of your image, you pass the command clip, and that rectangle that you define it as your area of interest will clip the image. So we can see in this piece of code how these clipped images look like. Yes.
What function only work with Eemont?
No, it works with Geemap, but here I'm clipping individual images. I'm not clipping an image collection.
Okay.
So for an image collection, we have to create a function. It's possible to clip, let's say, the entire archive, but we have to build a function, and inside the function is the command clip.
I tried to do that yesterday and done that.
Sorry, about the noise that we say that we have. And that's we are doing any action or something.
Say that again.
About the noise that we have, the lands that's
Noise.
when the stripe guys.
Oh, the stripe means no pixel data on that specific coordinate.
And we cannot do it.
We cannot do it. There are techniques to interpolate, okay? But those techniques are very empirical. There is, and that's the reason why NASA never filled up those gaps. They let it clean or without pixels because the values might or might not be correct.
So in case that's some of part of our cases studying lines. We cannot do it.
We can, I'm using them. So I'm going to show you how it looks like at the end. Okay. So here in the map, you can see the 4 images that I clipped. And you can see the stripes. Okay, so I still have information. I just need to be careful around those. Now, the following steps are commands that we saw it in the first laboratory, but this one will allow you to, it's the repetition. How do I export these clipped Landsat images out of Google Earth Engine? Let's say Google Earth Engine, too much coding. I need to memorize functions. I want to work in ArcGIS Pro or AirDAS or any other remote sensing package. So this is the command. First, you need to define a location where you're going to save it. So in this case, we go to our folder and look at the address. You are in, this is the home folder, the name of your repository, and you can put this in this folder, results step 1. And just to demonstrate that, I only have there my shapefile. I don't have any data. So I need to replicate this directory in this path. So I have this extra path here. Has to be machine learning applications / results step 1. Once you make sure that path is exactly where you want to save it. You run that cell, and then you run the next cells. The next cells are telling Geemap to export that image to that folder. And that total request byte must be less or equal to 833 files. Did I reduce again the... Oh, did you run the pip install Geemap?
Also, for this line of sight, the map.
So what I say is that my area or the size of the image is too big. But it's big because I added many layers behind. I added all the vegetation indexes layers to my images. So what I can do to simplify it is potentially select only the bands that I'm interested on. For this exercise, we don't need it, but we can do something like this. Select bands and close it. So what I'm doing is, instead of giving me all the bands, I'm going to select few of them. So let's see how it runs now. Attribute error, select band. I'm sure there is a select band. Oh, here. Okay. I should move this one. Select band. Okay. It's not allowing me to select the band for whatever reason. So we're going to run the next cell. The next cell is about getting the pixel data from Landsat to those points where I had my sample collection. So if you run that cell, it's going to create four files. Landsat for May 13, 29, 14, and 30. So this can be useful, for example, let's say you are also interested on getting pixel data for specific locations, and then getting that data out of Google Earth Engine. To review that, why it didn't allow me to do it. Okay, it's done with 2 files. Probably this is the command. Select. Okay. Okay. It's done with the 3rd file. We need 1 more.
I got an error on the last.
Let me see.
Sorry.
Now we got all the files. Where are those files? We go to our folder. Here they are. Here our, if we look at these files, they'll have the information of the every band, other bands information from Landsat. But at the very end are the indexes. Every index that is in the archive of Eemont for vegetation. So NDVI is here. There are about 60 vegetation indexes. So the question for us is, we have more than 60 vegetation indexes. We have the soil moisture values. Which of these vegetation indexes help me to estimate those soil moisture values? That's the question. Do I need 1 vegetation index, 2, 3, 20, all of them, plus also the bands? Which one? We don't know. And soil moisture, as we discussed it in class, is a variable that still we're investigating. Hydroblocks is making an effort, right? It still is not available like for everybody, like OpenET, we can download ET data now. But so that's the end of step 1, to create these files.
Step 1 is just used for providing data.
Yes, you have your CSV file with coordinates. The step to get it inside Geemap is to convert that CSV into a shapefile using RMap, ArcGIS Pro. Now with that shapefile, you can call it into Geemap with the command shape2ee. Now that those coordinates are recognized by Geemap, if I select an image, I can now extract it values to points. So that's the command. Geemap values to point. This is my variable of my shapefile, and this is the Landsat image. And I have to mention a name for.
And you added the vegetation index also to the Landsat.
Yes, I did that in here in this command. Landsat spectral field vegetations. So with that, I have these 4 files that now I can use to train my algorithm. If you open the May 29 CSV file, you will find that there are some rows with no data. Those are the pixels where those empty stripes of Landsat happened. So I had later to work on the regression. I had to deal with that later. So there are 2 ways to deal with that. One is I go file by file and eliminate those rows, or I can do it with code. So I'm going to show you how I did it with code, because doing it manually is also possible. Questions about this step? It's quite straightforward. The command that I was looking to export the image, it was, let me see, instead of select band, it's just select. I think if I run that cell now, it's going to generate me the exported images. They're going to be put in the result step 1 folder. You can see now that I have my first Landsat image already there.
Yes. For us to download them, do we? I mean, we have them because we cloned the data. I think mine's throwing errors, and I think it's because the file already exists.
Oh, yes.
It's a really long, super long error.
Oh, go to the results step 1 folder. And if there is Landsat data there, you can delete it. Delete the images and the text files and run the cells again. So now it's done. Now I have Landsat images out of the Google Earth Engine. All right. So that's step 1. You want to see step 2? Okay. You can open the step 2 notebook. We are going, when you want to do any regression effort, even linear regression or machine learning regression, the first step is to get the data. The second step is to understand the data. So here, what we're going to do is we're going to develop plots and statistics to see if there is any correlation between all the variables we have in those new text files and the soil moisture data. So we need to install a couple of libraries. So copy that cell and put it into the terminal. Once you do that, you can run the first cell pandas. So you can see that it's calling the cell, the folder results step 1, Landsat, pixels CSV. Like that, we keep calling the other 3 files. So now I have the 4 files, and you can see already in the second file, when you import it, you have a line that says not a number. That's empty data. Okay, so I have to deal with that. I have to figure out how to manipulate those not a number. So to see the names of the columns that I have, I can run this cell called print sorted data June 30. That's the entire list of all the columns present in the file. There are many. There is, for example, surface reflectance 1, 2, 3, 7. We also have the thermal data, which is STB6. The emissivity bands, quality control bands, we don't need it. But the first names up to here and some here below are vegetation indexes. So we need to clean up this list of variables. So in the next cell, I list what are the bands from SRV1 to SRV7. And also I got the list of the vegetation indexes provided by the Eemont algorithm. Why these are important? Because they will allow me to filter out from the pandas only the columns that are mentioned here. All the rest, I can toss it out. So this is how I do it. So I'm going to create a new file or a new variable. I'm calling my individual pandas variables. I'm going to be passing the command bands and vegetation, which is the 2 lists that I have, plus the soil moisture data, the name of the column of the soil moisture data. Since I have 4 columns, I'm going to assign to every Landsat date that I have, I'm going to assign its respective soil moisture column. If I run that cell, I have now these new variables. Now, if I'm going to combine them all, each soil moisture column in each of the pandas, the new pandas variables have their own specific names. I'm going to change it to a generic soil moisture. The next step is I have 4 Panda variables. I'm going to link them all together. The command to do that is the word concat. And this is the once I pass that, I run that cell, I have all my variables and columns organized, ready to be used, excepting for those rows where I don't have data. I haven't cleaned those up. So what we're going to do is we're going to pass a command called drop none. And we're going to set up the crop type as a category. So let's run that. And now, initially I had 80 rows. Now I have 71 rows. I dropped those lines where I have no pixel data. How many vegetation indexes I have? 91. So out of 91, plus the spectral, plus the reflectant bands, I need to figure out which ones are useful to predict soil moisture. Not all of them. So now I'm going to organize the data. I'm going to run a melt function. And with this melting, I'm going to start plotting soil moisture against band 1, soil moisture against bands 2, soil moisture against every vegetation index I have, the 91 vegetation indexes. So for that, I'm going to create a loop. So I'm going to call matplotlib as my function. And here I'm going to iterate. And I'm going to create a new plot as the iteration goes. So here I'm just plotting soil moisture in the y-axis versus reflectance data. Band 6 is temperature, and this is in kelvins. The horizontal axis is in kelvins. So the idea is I'm looking for a pattern, a linear pattern that helps me easily get a linear regression. I have a column that has crop. And with that column, I can assign colors to the points that belong to the alfalfa fields or corn fields or barley fields. So what do you think? Is there any linear correlation between soil moisture and any of the spectral bands?
Sure.
Do you see that the dispersed points describe a linear or a big non-linear behavior, or they're just scattered around?
It's hard to say, but on our seems like someone.
F4, for example, seems to have, but in the
Yeah.
bottom it's just spread
Yeah.
out. Okay, this is the soil moisture there is true data. So here it's all spread out. There is no pattern in the data. Here is also spread out, spread out, spread out. So if I try to fit an equation, the only one that seems to work is band 4, but all the others, could you pass any sort of equation? No. And that's the first step. Always when doing a regression analysis, even linear, you plot your variable against all the potential predictors.
Can we like calculate the correlation and decide based on?
Yes, you are in pandas now, so you can calculate the correlation, but always never stop plotting the data.
Yeah.
Correlation is good, it confirms the plot, but the plot is your major source of information.
Yeah.
Because the plot is going to show me a high correlation here, but it won't describe this dispersion of the data at the bottom. The next cell is going to go against the 91 vegetation indexes versus soil moisture. So if we run that, so we have to be patient because there are 91 plots that have to happen now. Because I'm now doing all the vegetation indexes. Because again, I don't know which vegetation index might be the most adequate to predict soil moisture. So what do you think? Any linear correlation or no linear correlation?
The NDDI is interesting. It's like a straight line. It's like,
And well, let's see. And here,
yeah,
the NDDI, we have some point here that this is skewed. Look, it might be a perfect predictor if it weren't for these
yeah.
two values. What about this one?
Yeah.
NR, FIR. Kind of linear, scattered at the bottom. So what I'm trying to show you here, and this is a part of any statistics class, before embracing a work on regression, always plot the data. So based on this, there is no clear winner.
Have the NDWI also in between?
Which one?
NDWI.
And let's see. I think that's a index for water. I don't think it's considered, but can be added too.
It's hard to see as well.
So no linear relationship clear a winner. There are some that seems to be potentially good, but nothing that you say, I choose this vegetation index and I can develop a linear regression there or any regression. So we're going to calculate now, as you say, the correlations. So I'm going to use this command that will take my pandas table, called soil moisture, and is going to look to correlate any other column against the soil moisture table. There we are. We have 97 values. Let's plot those values with sorted values by sorting them. So now you have from the negative correlation to the positive correlation, but you see that none of them, not even on the extremes, they pass the 0.4 value. So the correlation is weak. Okay? The correlation is weak. So there is no clear predictor. So far, all our statistics are shows that there is no clear predictor. Now, the beauty about regression is that you don't have to rely on one variable. You can put two predictors, three predictors, n number of predictors. So the hope is, despite we cannot get a single variable to be the predictor, I hope that I can get multiple of them to predict soil moisture. The question is, I have 97 potential predictors. If I build an equation that has 97 potential predictors, my advisor is going to fire me. Okay, because that's not real. So I need to trim it down somehow, especially if you can get down to 3 to 4 variables. That's more understandable than having 10 predictors in your equation. So this is so far how we have. Here we can see some of the bands. So the bands that are like at one end or to another end are the most promising variables. So temperature has the highest negative correlation with soil moisture. It makes sense. Wet soil has a lower temperature than a dry soil. After that, it says band 4, in this case for Landsat 7, is near infrared. Near infrared, well, let's remember, what do we remember about near infrared and vegetation? How it behaves, the near infrared with vegetation?
It reflects a lot.
It reflects a lot when there is, so this is the explanation. The more biomass you have, when irrigation happens or rainfall, this cover of leaf will minimize the evaporation, like because it's like an umbrella. Okay, so anything below the umbrella, the temperature doesn't increase much. So the higher the vegetation, the higher the soil moisture. So that is what is showing here. Then it's giving us other vegetation indexes that have correlation. We're looking at these first two. Let's look now at the other extreme. It's saying that these two vegetation indexes, especially the last one, has a 40% correlation with soil moisture. So there is potential that combining some of the extremes, I might get an equation that can predict. Now, we cannot just add and say 41 plus 32 plus another, I got my, no, doesn't work that way. But it's telling us all this exercise, there is potential to find a multiple predictor regression model. Okay. So, but so far we're exploring the data. We haven't done any regression analysis. We're just doing statistics and plotting. So now that we have that soil moisture file, we can now save it. Make sure it's saved in this case, results step 2. And then run it. You will see that in results step 2, that file where we clean up the data and only have soil at the reflectance and all the vegetation indexes, and at the very end is the column of soil moisture. So now I have my data clean and ready to try regression. But we will save that for the next session. Otherwise, I'll run out of material. Okay. Questions so far between these two notebooks? Okay, so now as we promised, is time to address questions of your term projects. Do you have questions about code in your third project, pieces that you found an error or you want to do something and you need help implementing it.